Terrific.
Yeah. Well, maybe we should get started. And good morning, good evening, good day, wherever you are. I'm Gang Chen from MIT. Welcome to MIT Innotherm Colloquium number 13. And let's go to next slide, Liang, please. So today we have a very exciting topic on thermal materials for building walls and the windows. And we know building consume large amount of energy, and those will be really interesting panel discussion. And you see, I'll ask our moderator, Nanyang Glicksman, to introduce our panelists. And I will just use one slide to introduce Liang. Let's go to next slide. So Liang is my colleague and senior, and he's a professor in building technology program and also in mechanical engineering department. He obtained his bachelor and PhD from MIT, master degree from Stanford, and has been a lifer. So we call people at the MIT for a long time, a lifer for a long time, since 1966. And he founded and was the head of the MIT Building Technology Program. He is an ASME fellow, ASHRAE fellow, and received the MIT Student Champion Award. And there are many other awards within this. I know, see, he and I received the Heat Transfer Memorial Award in the same year. So underneath the should certainly Heat Transfer Memorial Award. And his research areas including sustainable housing for the developing world, natural ventilation and aerosol dispersion, design tools for energy efficient buildings, thermal insulations, fluidized bed. And with that, I will turn to Nanyang. Nanyang, now you have the control for the rest of the session. I will go to background. Thank you.
Thank you very much, Gang. I want to welcome everyone to this latest version of the Innotherm Colloquium. I think we have a very interesting subject here. Again, the subject area on thermal insulation and advanced windows is particularly important because if we look at the attempt to go to zero net energy in all of our activities, buildings consume a considerable amount of energy. In the U.S., about 40% of the primary energy utilized in the U.S. goes directly or indirectly to buildings, and a substantial portion of that goes to appliances, building envelopes for heating and cooling systems. I have a couple of slides here just going on retrospective, what people have done in ancient times. First, a wall cavity filled what was called wattle and daub, which is a system of twigs and small sticks, which are then plastered with mud and straw. And if there are voids between the mud and straw, it has a substantial insulation effect. There's also a thatched roof, which has been used, and in fact is still being used in some buildings in the UK and other parts of the world. And again, this is a case where if the straw is put into the roof, there are substantial air cavities, which again form insulations, which makes the roof a very well insulated system. Now we can see in this particular case, though, the stone wall is not a very good insulating system. And in fact, one would have to go to something better to keep these poor people warm. And then finally, I want to show one slide here of the Apollo lunar module. And if you look at the lower half of that, the gold colored portion is probably one of the most famous vacuum insulation applications. This is on the moon, where they use multiple layers of mylar, which was coated with a highly reflective surface to essentially get very high insulation systems from that. I've often thought about, well, what can I say about windows in terms of past performance of windows? These are the two I came up with in terms of window control technology. in previous days. In the first, it's simply by using awnings or shading on windows, one could adjust the amount of solar input to the particular interior, but at the same time cut off most of the daylighting. So there's certainly trade-offs to be made there. And then finally, just the idea of operable windows and drapes or curtains which form some modest amount of insulation, again, is about the extent that people could do until probably the 20th century when they came up with double glazed kind of windows. So today we have a panel of 3 experts who have some interesting things to talk about, both in terms of insulation and in terms of advanced window systems. Our first speaker is Jan Kosny. I've known him for many years, starting at the time that he was at Oak Ridge National Labs. He's now a research professor, Department of Mechanical Engineering, University of Massachusetts, chair of the Technical Standards Committee in Phase Change Material Industry, Fulbright specialist, director of Building and Enclosure Materials, previously at Fraunhofer Center, which was in Boston, Massachusetts. As I said, Oak Ridge. Before that, associate professor at the Technical University in Poland. In his research areas, at a minimum, are building science, heat and mass transfer and porous media, materials for energy efficiency and heat storage, building envelopes, and building integrated solar technology. And he'll be talking today about vacuum insulated panels for use in buildings. Our second speaker is Elise Strobach, who's a recent MIT Mechanical Engineering PhD graduate. She's the co-founder and CEO of Aeroshield, an entrepreneurial research fellow at Activate. She was awarded the Ford's 30 Under 30 award in the energy sector, and there's areas of research including energy innovation, advanced materials, low carbon technology, and building efficiency. And our third expert is Dr. Yi Long, who's a senior lecturer at Nanyang Technological University in Singapore in the area of material science, a principal investigator at the Campus for Research Excellence and Technical Enterprise CREATE National Research Foundation in Singapore, a member of the Sino-Singapore International Joint Research Institute, and her research areas include energy-saving smart windows, smart materials and devices, thin films, nanoscale structural materials, and nanofabrication. And we'll hear some of her work on some of the advanced window control systems. So at this point, I'll turn, let me make just one thing in terms of our mechanics for today. The presentations will take probably about 40 or 45 minutes. That should leave us some time for discussion and for a wrap up. If you'd like to submit questions for the panelists, use the question and answer button in the Zoom over here on shown on the right here. We'll pulling for that screen, and we'll take some of your selected questions and direct them to the panelists. This colloquium is being recorded, and if you want to, you can go to YouTube and look at a recording of if you want to review some of these things. And certainly there'll be questions we cannot get to, and we'll try and post answer to those questions at that particular point. So at this point, let me turn it over to Jan, and he can tell us something about his work on vacuum insulation systems. Jan?
Hi, how are you? This is Jan Kosny, and I would like to welcome everybody for my presentation and for the whole colloquium. I'll be talking about vacuum insulation. I have a question to you, Leon. Do you see my screen okay right now?
No, I'm just seeing you. I'm not seeing your screen.
Oh, it's coming. Okay, let's try to. Now it's okay?
No, I'm still seeing I'm seeing your screen. You should push where it says share screen. Have you done that, Jan?
Yeah, I did this. Okay, let me do this again. System asked me if I want to stop sharing the screen. Okay. I see your screen right now.
Oh,
Now?
there we are.
Okay, sorry.
Now
for the
you
call.
need to go in full screen mode.
Yes, okay. Okay, so welcome everybody, and we'll be talking today about vacuum insulations, and here's my agenda for the talk. I will be talking about vacuum insulation panel thermal effectiveness, core materials, membrane barriers, improvement of the vacuum insulation long thermal durability. I will be talking about edge thermal losses in vacuum insulation panels. I will talk about little bit about building application, real full-size building applications, and at the end I will try to give some economic reasons for wider VIP applications in the buildings.
Yeah, it would be great if you can switch the display as your top middle, because it's your own view now. Yeah.
This is okay?
Yeah.
Great.
So what are VIPs? VIPs are small pieces of insulation usually made as panels, and they have three major components. First component is core material, which is open cell, open pore material. The second one is missing air in those pores, that means vacuum. And third one is membrane, which holds all the exterior air from coming into those pores within the vacuum core. The vacuum level within vacuum panels is somewhere between 2.2 to 3 millibars, and thermal conductivity, center of the panel, thermal conductivity of vacuum panels is somewhere in between 2 to 8 milliwatts per met Kelvin. It is very important that vacuum panels are used right now in many different industries in the US, and that usage is coming with the many different requirements. The major requirement is the high thermal performance. That means high R value, very low thermal conductivity. With that slide, I would like to actually, in very few words, try to describe, which probably will take a couple hours of theoretical lecture to fully understand. There is on the right side, there is a chart in between showing relation between gas pressure and thermal conductivity. And it is showing that relation for several types of materials, coming from very low size pore materials, like for example, aerogels, going back left side into the materials of much higher size of pores in the range well over 100 micrometers. The major message from that chart is that materials with very low size of the pores, well below 1 micron, they need much less vacuum to perform very well, to reach very low level of thermal conductivity. Materials of higher cores, of higher size of the pores, they require much higher level of vacuum to reach that good thermal conductivity. And you can see that actually materials of higher pore sizes, they increase their thermal conductivity in the vacuum level in the neighborhood of 1/10 of the millibar, while aerogels can do this still up to 100 millibars. This is the major message about thermal conductivity of the pores as a function of vacuum level. There are many different core materials in use right now, with fumed silica being probably #1 and most common. The reason is that fumed silica powder is giving very low size pores, and as I said before, they affect a very low level of thermal conductivity with reasonable levels of vacuum. Another group, very interesting group of materials, are fibrous materials with fiberglass and mineral wool. They have quite a large size of pores, but that's interesting, they are non-flammable, they perform very well on high temperatures, and they can achieve in very high level of vacuum, extremely high levels of thermal insulation. Another group is a number of collection of different powders, and I don't want to move too much on this group, but they can have pores coming from the nano size into the high micron size. Interesting on the most promising materials from that group is diatomites and fly ash. Fly ash for two reasons. One, the size pores, size of the pores. The second one is that the fly ash can also opacify the other materials. Opacify means that can reduce radiation heat transfer. Another group, very inexpensive potential core materials is they are foam materials, open cell forms. Very popular, very inexpensive, easy to produce. Problem is that they have pores in the size of 200, 300, even over 300 microns. That means they require a huge amount of vacuum. Not very good for long-term usage of vacuum panels. And emerging technologies, there are aerogels, which are having pores well below 100 nanometers, and those materials perform extremely well. Problem is that they are expensive in production. Regarding the cost, specific cost of fumed silica is about $2, a little bit over $2. Recently in Europe, several European projects were focused on development of lower cost, and actually they reached about 70 cents. So cost was reduced 3 times. Not necessarily with the same quality of the vacuum core material as fumed silica. Talking about external envelopes, I must say that the major function of the external envelope is just mechanical protection of the core material. The second major function is protection from the ingress of gases inside of the panel. There are several applications of VIPs in different industries, and each application are coming with different lifespan. For example, shipping container is used like 15 to 20 times within probably 1 year, maybe year and a half. Building component is used for lifetime of the building, and it is not lower usually than 50 years. And you can see I listed on the right side IEA requirements for the permeability of the membranes for vacuum panels, considering 50 years lifespan. On the right of the left side, I listed oxygen transmission rate and water vapor transmission rate for typical 3-layer aluminum coated foil, which is used as a membrane for vacuum insulation. You can see that actually there is like 10, 15 times different parameters. And that means that there is a long way still for industry to meet those 50 years lifetime requirements for those panels. Another big important factor is that this membrane, which is covering the core of material, has to be sealed somehow. And that seal, design of the seal and the components of the seals are very important. And actually, it's good to remember that about 50% of the permeance, gas permeance, into the panel sometimes is just dedicated to the seal quality. How important is heat transfer through the edges? You can see on this picture how panels are connected. They are bound together in buildings. Please remember that building constructions are using different connections, like for example, shipping containers, when panels are connected on edges only, and design of the edges can be different. We have 2 types of heat transfer, one central of the panel heat transfer and edge heat transfer. Usually we use a linear thermal transmittance coefficient, which expresses that heat transfer on the edges of the panels. Edges, quality of edges is a long story and depends on the application. They can be designed in different way. Here I gave just a couple designs of edges which are typical for buildings. And actually that center design, what you can see with rough surfaces put together, it's probably most typical situation. What's happening here, we have several vacuum panel materials, and because those surfaces are not even, there's a lot of air in between a panel. The most ideal situation is when we have just very detailed connection between panels. Talking about membrane materials, historically, aluminum was the major application as a membrane for the first aluminum foil in the earliest application. Later it was it was replaced by less conducting steel, stainless steel, and then in super applications right now we are using titanium alloys, which are less conducting than stainless steel, but they are 10 times more expensive than the stainless steel. So there is always cost of the thickness of the material, price, and the level of that material can protect vacuum. Typically, when we go into the lower cost materials, right now, the very common application for building vacuum panels are several layers of the very thin layers of the aluminum foil, which are sandwiched together. Why several layers? When we go to the very thin layer of aluminum foil, we will have imperfections. That means small pins where air can go through. If we assume that we put like 3 layers together, it's a very low chance that we can overlap those small pinholes, those small holes when air can penetrate through the membrane. So this is the matter of the cost and the matter of how much metal we are putting on the membrane, highly conducting metal. To reduce conduction, people designed the plastic foil layers, which are aluminized. So we deposit very thin layers of aluminum. It is somewhere between below 20 microns. And usually people are using 3 layers of aluminized foils to create the membrane. How good they are? They are worse than really sandwiched thin metal layers, but they are better from thermal conduction and less costly. The emerging technologies right now, there are plastic membranes. When people are using the inorganic oxides as a deposited to create the barrier film. It is a new technology. There are several companies working on this. Technology developed mostly for the photovoltaic, as a backshield for the photovoltaic applications, but it's finding its application also on vacuum insulation. Seal. Vacuum seal, it is something which is very important. Typically, because of the technologies coming from historically from food industry and pharmaceutical industry, those seals have been placed on the edges. As I said before, we try to minimize amount of the conducting material on the edges. Those seals are either folded different way out of the edge or placed completely in different applications. That's very critical for design of the vacuum panels for building applications, to minimize the amount of the conductive materials on the edges. If you don't do this, you have situations like here, and I have to say, this is my design, this is my building, this is one of my first buildings. I didn't have much choice. I had, at that time, vacuum panels which had seals located on the edges. You could see the results. Another situation is somebody purposely screwed up with design. That means that you could see on the right side, there is a number of vacuum panels which were created in the board. And that board is made in the way that there's a lot of space in between vacuum panels. That space was filled with foam insulation. Foam insulation, in case of vacuum panel usage, creates thermal bridging. And on the left side, you can see proportions between thermal conductivity. For example, between vacuum panel and aerogel, it is 3 to 5 times. That means that even aerogel can create, in that case, a thermal bridge. Talking about real life applications, my team and myself have been involved through years in several building designs. Here is the Boston historical triple-decker when we designed the whole roof using vacuum panels. It took a lot of thermal analysis, structural analysis, hydrothermal analysis to design those roofs. Here is another building when actually this very good example. It was showing that the location of the panels of the elevation cannot be just by accident. Usually in those works, this has to be done special mapping for the whole elevation, and not single panels, but several panels have to be used to fill the whole elevation. It is quite complicated work, which involves also advanced thermal modeling for making building details and making cost economical analysis. One very important fact to remember about this: vacuum panels can be only cost effective as long as they are used in smart way and designed in smart way. If they are used randomly, they are too good materials that the whole value can be wasted. Here's a couple slides about the testing. I don't have time to talk about this. If somebody will have questions about the testing of vacuum panels, please contact me directly. I would like to stop here on the cost analysis, because for years we tried to justify using of vacuum panels using energy calculation. It is very good attempt, but not very successful. The major value coming from using vacuum panels is space. I'm giving here example when we use office building with floor plan 43 by 43 meters with thermal requirement for wall using US units R30 in SI 528. Difference in thickness between vacuum panel and polyisocyanurate form is about 127 millimeters, it's 5 inches. That means that across the whole floor for that building, we are saving 23.4 square meters of the area. That area has value, and you can see that in different places around the world, that floor area can have different value based on the real estate values. In Monte Carlo, we will be saving $1.4 million because of that space area per floor. In Washington, DC, we are saving $140,000 per floor in that building, assuming that average price per office space in Washington, DC is around $6,000 per square meter. So if we assume that we gained $140,000 and our vacuum panel cost about $30,000, you can see I'm using here on this chart, on this specific slide, typical vacuum panel prices with ranges in the US. This is not everybody's paying, but I've been doing this for many years and I have very good access to manufacturers of vacuum panels around the world. We can see that actually the highest typical price for me is about $80 per square foot. The total value of the used vacuum panels will be $33,000 for that specific building. We saved $140,000 on the floor area, so it leaves $107,000 for some other cost or for the profit. At the same time, the cost of using typical, the same R value foam insulation is about $12,000. So that material can be cost effective. Question is if we can justify this in the right place, and this is a good scenario for using this. It has to be high R value requirement and high cost per floor. That's at the end of my presentation. I would like to, at the end of the summary, tell that we have to always remember that vacuum panels have a lot of different applications, and each application is coming from specific recommendations and requirements for those panels, which are coming with special designs. So panels are not identical. The most critical factors which are coming with the market value is nominal R value of the panel and price. The second factor is panel durability, which is strongly related with the core material and design of the seals and membrane materials. I would like to focus also on one very important fact, which is talking about packaging of the materials. That means that installation, the way how panel is installed. Packaging is can reduce performance, but even 50%. If there is incorrectly packaged vacuum panel or incorrectly installed, nominally R50 vacuum panel can become R25. It's very easy. That means we are losing a lot of money. New future research areas for the panels, vacuum panels, will include low conducting membranes, new VIP edge designs, new materials for VIP core with special focus of nanomaterials, new method of protective packaging installation methods, and enabling structural members allowing vacuum panel applications in buildings. That concludes my presentation. Thank you very much for your attention. I'm ready for questions.
Thank you, John. We'll put the questions off till the end of all three of the presentations. if you'll now
I will
stop sharing, and then Elise can start with her presentation.
Great, we'll get set up here.
It's okay?
Does that look good?
Terrific.
Excellent. Well, thank you. Very excited to be here today. So my name is Elise Strobach, and I'm the CEO, founder, and inventor of Aeroshield. And we make nanoporous glass insulation for energy efficient windows. So we spend about 80% of our lives indoors. And I think for some of us right now, it might actually be a little bit higher percentage than that. So I think we can all appreciate the importance that windows have in our buildings. It's not just about the energy bill, it's also about our thermal comfort and our productivity, which is why, the window products that are available, it's so important for us to have diverse solutions for our buildings. And, one piece has got into this industry in particular. I'll talk a little bit about my background later, but when we look at the market today for windows, what you start to find is there's this pretty large divide when we look at the performance things that matter to us, like affordability. So the cost that you have to get that performance into your home compared to how that window performs thermally while it's installed for 20, 30, 40 years. And in today's products, actually, most people, more than 80% of new products are this double pane class, where you see that it's incredibly affordable, but it's not the top efficiency. And this really kind of hits at this core problem that new homeowners have to choose between sustainable products and cost-effective ones. And that's something that, personally and through founding this company, we really want to address this problem. We want to offer new solutions that can hit at that affordability and efficiency that we really need to drive adoption of cleaner technologies. Now, the way that Aeroshield is doing this is by using an amazing material. So Jan nicely kind of started to introduce some of this topic. So Aeroshield makes a super clear aerogel. Now, when we look at the sheet, actually what you're seeing here is pure glass, but it's glass that's made up of tiny little pores, actually 95% pores that are so small because we've engineered them to be smaller than the wavelengths of light, which means the visual experience is comparable to glass, but you get this amazing thermal performance. And it was understanding the structure, which I'll talk a little bit about during my PhD at MIT, that really allowed us to understand what we needed this material to do, not only from a fundamental heat and light transport mechanism, but also how we deliver that innovative material to buildings to make them really impactful. And so the way that Aeroshield found to do this was by taking the traditional design and manufacturing process and designing a way to bring our material, produce it. We're currently working to scale it up so that it can be ready to integrate at initial manufacturing right in that step and be ready to deliver with amazing performance in the same form factor that we're really comfortable with in our homes. So by, again, taking this traditional double pane solution and adding this thermally insulating material, we can create a product that is paying back, 5 times faster than comparable performance products on the market today. That's really exciting because we want to be able to let people make better energy efficient solutions, because our buildings are a huge contributor to greenhouse gas emissions. So if we look at a thermal image of a building, we actually look at how much energy loss is coming through these windows. It's a big problem, and it's a tough one to solve. And for that reason, $40 billion in energy is lost through our windows every year in the United States. Now, when we think about how to solve this problem, it's not just about, the amount of heat that we're losing through our building, because we can make a super insulating window, but it also has to have that cost effectiveness. And now that's tricky to bring because the kinds of materials that we have that can address this complex heat transfer, it's not just trying to let the light in, trying to let us see out, but it's also trying to stop conduction, convection, radiation, and put it into a design that can be delivered and plugged into really, really diverse types of buildings and locations. So you can kind of start to appreciate now that the reason that these losses are so high is because it's not a simple problem to solve. So one of the materials that has often been looked at as a solution to this is this class of aerogels, this super insulating material that, as you can see here, has this amazing performance. So again, can be incredibly lightweight, can be molded into custom shapes, you know, and has all this super insulating performance, twice as insulating as air. And that's really exciting, except when I look at these pictures here, one of the first things I see when I say, do I want to put this in my window, is that does not look like my traditional glass. And so for a long time, this material has really not been developed the way that I feel that matches its potential, because it has this super insulating, but it doesn't have that nice clarity. And so in particular, that was something during you know, my work at MIT that we really started to look at the mechanism for why these aerogels were not super clear. And actually, we stole some modeling straight from the way that the atmosphere works. So on a hazy day, when you look out, the difference between these two pictures, I know which one I would want in a new window, and it's certainly not the one on the left. So understanding the fundamental nanostructure that causes an aerogel to be clear or not was a really important step. But we also had to do it by understanding this nanostructure to improve that clarity, but not lose all that great thermal insulation. Because as Jan actually already started to allude to, aerogels are not as cheap to make as glass. And so we have to be really choosy with the amount of performance that we're paying for, with not only the cost that it makes to make this material, but the energy that you embed when you make it. Because again, we don't just want to make something that performs well for the first year. We want to make something that is more sustainable throughout the lifetime of that building. So it was really exciting that as we developed and we made this understanding of the nanostructure and explored more and more how to fabricate and what the needs of the industry were, we started to be able to map, you know, what kind of material we needed to make to balance this cost, this optical quality, and this thermal insulation, so that we can try and deliver as much impact in application as possible. And I think one of the most interesting things that I've learned is that windows are not just something that you find in residential and commercial buildings. So it's a really great place to understand the importance of that thermal problem. And, you know, we experience it every day, but it turns out we experience windows in a lot of places every day. You know, refrigerators, your grocery store display cases, ovens, medical and industrial equipment, and our transportation vehicles all have windows that are important to us. And all of those windows can be made better by aerogel. And so Aeroshield's goal is by being able to bring a material like this to market, we not only can impact our direct application space, but there's opportunity for innovation in all of these places. I just kind of want to briefly bring a nod to my team, because I think that one approach that we've taken in particular is to really focus in on the value that we can bring as quickly as possible. We feel that, you know, one, the potential of this breakthrough that we've had based on the technology at MIT, really, it has an important home, you know, in this industry and helping us get to better performance. But the other piece is that it's just been a really interesting experience to go from the material development fundamentals to looking at how you actually get that application. And I can't stress enough how it takes really a village to make a technology like this successful. So we're working with people, you know, window manufacturers, glass manufacturers, you know, heat transfer experts. How do you install these pilot products and assess whether they're really doing what you expect? And how do we take that information and make it better? And how do we try and prove that a new product that's really never even been in the market for a year in the form that we're making, how do we prove that that's going to last in your building for 20 and 30 years? And it turns out there's a fantastic ecosystem that has been looking at these problems for a really long time. And I just want to share that, you know, we're very passionate about it, and there's lots of very passionate people out there. And all of them working together in concert, I really believe, is the way that we can get to this next step. So Aeroshield in particular spent a lot of time in the lab, really setting up, I think, a strong foundation. And right now we're transitioning into pilot mode, where we can actually demonstrate the manufacturability and the practical considerations for bringing a technology like this to market, with the goal of being able to supply some first really niche markets in late 2022. And that's particularly exciting because I do personally really feel that this technology can have a big impact, you know, looking at not only, you know, increasing the comfort and reducing your energy bills in your homes, but just creating a more sustainable, valuable infrastructure that's more effective with the energy and the cost and the time that we're putting in to the things that we're using, and really getting this full performance out. Yeah, so really big potential here. And yeah, really excited to get the discussion, but that's all I have for now. So I will pass it back over to you, Leon.
Thank you, Elise. Yes, that raises a lot of interesting questions. I think we can pursue in the discussion. Well, why don't we go ahead with Yi? Would you?
So can you see my screen now?
Yes.
Okay. So can I start?
Yes, please go ahead.
Okay. Hi. Yes. So I'm the only material scientist here. So I don't talk about heat at all. So I'm only talk about smart window. So basically, I start with a background. As Alice have already said, that the window is the least energy efficient part in buildings, and building is really the major culprit of global warming. And there's four type of smart window. So electrochromic, thermochromic, mechachomic, and the photochromic. Okay, so based on the stimulus, there are four types. So based on their characteristics, so we summarized in our recent review, thermochromic is what we are doing here. So because it has a passive actuation, and the stimulus is coming from heat. So basically you can imagine just winter and summer, because temperature is different. So it's going to respond to the environmental temperature automatically. So it's a thermal stimulus. So it's very simple coating, and it's quite suitable for energy saving windows compared with like a photo, because photo you can imagine, because it's based on the UV. So in winter it's also going to block the sunlight. So that's not preferred. And the optical transition speed is acceptable. So I focus on the thermochromic. So in the thermochromic, so the principle is very, very simple. So basically we just let the solar transmission to come in and warm up the house. And in the summertime, we want to block the sunlight. Okay, it's very, very straightforward. But please bear this in mind, the performance assessment. So there's big three things. Okay, so far we have a big three things, which is transition temperature, since as I said, because we need this temperature which is reasonable, so about 30 degrees should be very good. So transition temperature, so this is number one. And the luminance transmittance, because it is still a glass, so we have to make sure the luminance transmittance should be good enough. So, and also there's another one which is solar modulation. So you can imagine the solar transmission difference between the summer and the winter. So obviously, so in summer you want less, in winter you want more, am I right? So the difference is bigger the better. So please bear this in mind. So we need to reduce the tau C and also increase both luminance transmittance and the delta T sol, okay, solar modulation. So these are the big three things in thermochromic smart window. So actually in thermochromic smart window, so there are also a few categories such as hydrogel, ionic liquid, metal materials, perovskite, liquid crystal, and vanadium dioxide. So vanadium dioxide is the most investigated materials, okay? So, and also you can see we have done review on this one. So what are the characteristics of different categories such as hydrogel and ionic liquid, and some of these, they have the color, the transmittance problem, because it's going to change from opaque to transparent. So that's sometimes some customer does not like it. And the vanadium, the good thing for vanadium is there's no appearance change during the transition. But there's a problem with very high tau C, which is 68, so you have to reduce. And also the vanadium dioxide is not very stable, because it's not the most thermodynamic stable phase. And also the thermochromic property, which is very bad. So I just summarize here. So in smart window, we have four types. So I only focus on thermochromic. And in thermochromic, we have this many. So I will also only focus on vanadium dioxide and hydrogel. So you can see this blue one is what I'm going to talk about today. Okay, so for the vanadium dioxide, so what's the principle behind it? Simply just because across this tau C, so there will be a semiconductor to metal transition. So which means you can imagine at higher temperature, it is more or less like metal. At lower temperature, it is more or less like an insulator. So this make it optical property change completely. So this is one type, which is vanadium dioxide. So the other one is hydrogel. So hydrogel, the working principle is a little bit different based on the phase separation. So you can imagine this is polymer chain. So once it heats up, so the polymer chain is going to shrink. So once it shrinks, so it's going to become a scattering center. So it's going to block the sunlight. Okay, so that's are the two principles of, as a material scientist, we have to know. Okay, so these are actually what we have contributed in this community. So in the vanadium dioxide, so we have contributed a few ideas such as these biomimetic mosaic structures, photonic crystal structures, and graded structures. And also hydrogel, we're the first one in this community to introduce this hydrogel, which is organic materials, so into this smart window. And because each of them have different issues, so we add another factor, which is active control. Like in hydrogel, we're trying to combine with dual heating, with transparent heater, and trying to give it electro-thermochromic, which means, because as I said before, thermochromic, which is passive, but we give it a little bit dual heating, so we can make it both passive and, and auto also. And also, to further enhance the properties, we have another stimulus which is coming from the mechanical stimulus. So combined with dual mechanical and thermochromic, so we can further enhance the properties. All this with aim to enhance the thermochromic properties. So please remember here, so what is thermochromic properties? Basically, is reduce tau C, number one. Number two, increase TU, which is luminous transmittance. And number three, which is increase the solar modulation. And the last one is just some hybrid. This is very material science. We combine the organic and inorganic together to get a maximized energy saving. Okay, so I start with the first one, vanadium dioxide. So we actually have a review paper. So if you're interested in this technology, you can just read through. So basically review what is vanadium dioxide from electronic scale to this atomic scale, and then to this nanoscale, then to this lab scale, and also the architecture scales. Okay, so and also these are the properties summarized. So you can see that, as I said, three things: TU, delta Sol, and tau C. So because for the vanadium dioxide, so the tau C is pretty high, 68, so we have to reduce it. But when you reduce it, you're going to sacrifice TU and delta Sol. So it's not easy. So you can see the highest delta Sol is roughly about 30. So it's pretty low actually compared with other categories. Okay. And I just give you one example we have done. So we use this tunable plasmonic effect because, as I said, vanadium dioxide change from metallic phase to insulator. So which means they, at the metallic phase, they are going to have a plasmonic resonance. So why we need to tune this? Because you know this, we have to shift the peak to a dense solar energy area. So which is here. So we're trying to shift the peak of this metallic phase. Also, you can see we have used some method to make this dotted nanoparticle, nanopatterns, and we are the first one to report this tunable plasmonic effects because this is quite important for the solar modulation. But even so, you can see with such a lot of work here. So this is the plasmonic tunable structures compared with others like composite, porous, material, biomimetic structures. So it's more or less like comparable. So as I said, it's really for vanadium dioxide. It's really due to its physical limitations. It's difficult to further enhance its thermochromic properties. That's one of the reasons why we switched to hydrogel. So because hydrogel in vanadium dioxide, they only modulate in the infrared range. They don't change with the visible range, okay? So they only modulate at the infrared range. But infrared range, the energy density is pretty low. So we think, hey, maybe if we tune at this visible range, maybe we can enhance this delta Sol, which is a solar modulation. So as we predicted, so it's very obvious. You can see when we increase temperature, so it's going to change from very transparent to sort of like translucent or opaque. And you can see if I compare with vanadium dioxide, the delta Sol is nearly doubled, and also the TU is also increased. So this is very first paper of hydrogel in the smart window, thermochromic smart window. Then we further on, so we just composite with hydrogel with a silicon luminate gel, which is organic inorganic gel. So and we can enhance its printability, 3D printing, and also with a much better water retainment because we need a very good durability. Okay, and this is we just combine, so you can see this red one is vanadium oxide. Okay, so the black color one is hydrogel. So once we put a hydrogel and the vanadium oxide, so we can both open up in the visible range and the infrared range, give a record high TU and delta so at that time. Okay. And also this is by Nicholas Fang from MIT, and I think it's last year, right? He reported also hydrogel is pretty much the same, and in Joe, so you can see it's very much opened. So compare with our silicon aluminum hydrogel, so ours is here. So Nicholas Fang's one is roughly here, but you can see compared with vanadium oxide. So vanadium is here, vanadium, so the delta so is at most 30 to 40, but for hydrogel it's very easy to reach to 80 or 70. Okay, so the solar modulation is the most important index for energy saving. Okay, so but the good thing is that, okay, good thing for hydrogel is have very large solar modulation, but the problem is one state it is opaque. Okay, so some customer may not like it. So and also in this Tibun here, what he included in this summary, actually this is only one temperature, which is you can imagine it's winter. Winter, okay, have very high luminous transmittance, but you can see at the summer, so it's completely blocked here, visible range. Okay, so this is not preferred for some customer. They want visibility because whatever is their window. Okay, so as I said, since the hydrogel and the vanadium oxide both have its issues, so we propose this active control technology. So this is the first one. So we combine with this transparent electrode, use a big draw heating, give this first thermal thermochromic. So it's a dual response. You can say I give them a little bit input. Okay, so you can see you get opaque. Okay, this is a little bit like electrochromic. Okay, so this is our first work. Then we just further modify our recipe. So you can imagine these are the silver here. So we put our hydrogel. Actually, this hydrogel is hybrided with silica gel. So once this hybridation, so we can even put this hydrogel. You can imagine there's a lot of water there, just around this silver nanowires here. So by doing so without short circuit, and we can very good this bending. We can have this 180 bending, and with much faster response time, and also much less applied voltage. And also you can see we can even twist because this is hydrogel, so you can use as a light guide. So since this is a very flexible forms, thermochromic forms. Okay, and then this is our little work about this because we need this transparent electrode to give draw heating. So one of my research fellow, Hebing, he come out with a very simple message, just simply by stirring. So he can align this silver nanowires monolayer. Okay, this is just one layer of monolayer of silver nanowires on top. So by doing so, we can get the highest transmittance, nearly like 80, 90, highest transmittance, highest conductivity, okay, and highest stretchability. Okay, so this is also part of this work. And okay, so then as I said, vanadium oxide, the maximum delta so is roughly, even the theoretic value is roughly about 22 or 23. Okay, so there's and also because it's very absorptive at both stage, at high temperature, low temperature. So how can we further enhance? So my student Yu Jie, he come out with kirigami structures, just use another stimulus which is coming from the mechanical. Okay, use kirigami structures. Okay, so you can see without kirigami structures, so we have state 1, which is summer. Okay, state 2 is winter without kirigami, and once we have a kirigami, we open up. So this is winter. So state 3. So obviously you can see with you combine with this thermochromic and the mechanical kirigami chromic, okay, at these two together, we can largely enhance this TU and delta so at the same time. Okay, and also you can see this is comparison with other vanadium oxide. So this work, which is much better and even much better than separate value. Okay, also this is the first paper start to use NH+. working with a civil engineering professor. So we're trying to understand how much energy saving we can have. Okay, so this is a very first work to include this energy saving performance using Energy Plus. Okay, so I quickly move to perspectives. So this is our review paper. So I work together with my colleague Pussy. She's expert in electrochromic. Jie-Ying, he's an expert in this mechanical chromic. So we just come out this paper together. So since, as I said, there are 4 things there. So what is the next? So we said we have thermal, we have electrical, we have mechanical, we have photo. So we should break the boundaries between each other. So by giving them dual stimulus, we may largely enhance these properties. Like my group have already done this electro-thermal technology, and also mechanical chromic plus thermochromic, and also some other work combined with solar cells. Okay, so these are the perspectives in the whole smart window technology. Okay, and also this is another work, just published actually just a few last months, and we add another functionality in Windows. Okay, so by just use this as squid, so you can see the squid. If you see these structures on the surface, so actually when the squid getting very nervous, so it's going to change color automatically because there's certain strings that change the microstructure on the surface. So we borrow this idea. So we come up with the concept. You have this window not only save energy, but at the same time give privacy. Okay, so how does it work? So simply when your eyes can only see the pointed light. Okay, but energy saving to receive all sorts of scattered light or whatever. Okay, so by simply using 2 modes. So this is a strip 1, just a pointed light, and also this is scattered mode. We use intersquared spheres to collect all the sunlight, so we can separate the energy saving mode and the privacy mode. Okay, so you can see, so this one is the energy saving mode, and this is the privacy mode. Okay, so can I give you a video here? So this is privacy mode, energy saving mode. So when we just stretch it, so it doesn't change, it will change the privacy. Okay, but the energy saving does not affected by this. Okay, so this is a very first one, a very new paper, and also there's another paper by Professor Yang Pei-dong from UC Berkeley. He combined thermochromic with some perovskite solar cells. Okay, so why they do so? As I said, because the window have large areas. You can imagine, especially in the urban area. So when the window has such a large area, so people want to make full use of it. So why not? We have energy generation plus energy saving at the same time. Okay, so Prof. Yang Pei-dong from UC Berkeley come up with this idea. I use this perovskite. Actually, at low temperature, you can see it's winter, more or less like let the sunlight coming. Summer, it just block the sunlight. Okay, actually, this is very much POC. There's a lot of issue there. So number 1 is just like low temperature. There's no PCE at all, which means it doesn't work. Does not work as a solar cell. Okay, it only works at higher temperature, so it's about 7, even less than 7%, right? So this is very low. And also the other one, this high temperature, this transition temperature is about 107 degrees. So it's too high. Okay, obviously, right? So you can imagine for a good window response, you have to roughly tune it to about 30, 40. You know, that's reasonable. 100 is really too high. Okay, but this is a very good POC proof of concept paper. Simply combine energy saving and energy generation in one functionality. And also in this review paper, we mentioned about the problem for this smart window. So high cost, durability, any material, since you can, if you want to put on the window, it have to be like 20, 30 years. And also the energy saving maximization. It's very unfortunate in my research community, actually nobody talk about heat. Nobody talk about heat. Everyone just talk about solar modulation, which means we only modulate the optical transmittance, which is about 380 to 2500 nanometer, the wavelength of solar transmission. Okay, but it's weird. I don't know why, my research community never think about heat. So that's why in this review paper, I wrote more comprehensive energy calculation while this multi-interdisciplinary collaboration are needed to understand the complex heat transfer. So we need the collaboration from all of you, from other fields, to make our research much more advanced. Okay, so again, so this high cost, just like my friend, Prof. Jiang Xu Chuan, he was a Monash professor. Now he moved to Jinan University. He come out this very interesting. Oops, yeah, it's a, sorry, maybe okay. So this is a photochromic. They are trying to sell it to this how to say, the agriculture. So I just put this slide here. Nowadays everyone talk about urban farming, right? The urban farming use this greenhouse. So nowadays actually in the Europe country, all the greenhouse actually now is a window glass. So the good thing is these plants they really enjoy this blue light and the red light. Okay, so they selectively enjoy the blue and red. They don't really enjoy this green color. Okay, so so there's a large room here for people to not only save the energy for the window. That's number one, and also there's another one is trying to promote the plant rows. Okay, so this is another thing we can further move on. So as I said, the urban farming is another research area which is going to be very prosperous. Okay, and also since as I mentioned about durability issue, one of my friend Cao Xin from CAS China, he come out some ideas using this hydrogen oxide, right? Okay, it uses coating and on top of vanadium dioxide, and they do this X-ray test, and they found this vanadium dioxide can last about 18 years, if I'm not wrong. Okay, so this is also some very milestone work here because vanadium dioxide is not very stable. So this is something we can further move on. And okay, so this is actually the ending one. It's just my paper published 2 days ago, so it's really fresh baked. So I think this is the first paper to include the thermal factors in smart window. Okay, it's a very simple concept. So water, right? The water has one of the highest specific heat capacity. You can say water is here, so nearly the highest one. So hydrogel. So a lot of people doing hydrogel. Actually, hydrogel is 96% water. So we're saying, hey, everyone is doing like gel like semi-solid form. So why not we make use of this high specific heat capacity characteristic water together with this optical modulation of hydrogel, so we make a liquid. So can you see here? So this liquid, right? So now it's not gel anymore, okay? So it's a liquid form. So this is a liquid form, so we can pour in between the glass panel. So make this process super easy, for any window. It's very difficult as a material scientist to make it uniform, okay? So please bear this in mind. So we put this one, you can see, you can imagine if this is winter, so it's very transparent. So if it's summer, it can be very opaque or translucent, okay, depending on the compositions. Okay, and also we have done a bit of this thermal test. So you can say compare with normal glass. Normal glass is here. So once you have thermochromic pass a little bit of thermal capacity, so we can reduce the temperature dramatically from like 85 to about 55. Okay, so this is number one. The other one, I think Yang must be very familiar with this, the phase change material, why people use phase change materials. Okay, actually it's not phase change, but it's more or less like a thermal storage materials. So we can make this peak shifting. So this is actually very important for phase change material because peak shifting, you can imagine if all the window, the peak happened at 12 o'clock, but if we can shift a little bit to like 2 o'clock or 3 o'clock, this very meaningful for this electricity grid. Okay, and also we have done this winter test in Beijing. Okay, so you can see once you have once you have optical modulation plus this thermal storage characteristic. Once you have these two together, so you can have a bit higher temperature. Of course, this is not that much, but still a little bit higher compared with normal glass. Okay, so this is our very, very new paper. And also we use NH plus again to calculate whether our things is really NH saving. Yeah, it is true in Shanghai, Las Vegas, and Singapore, you can see. So all these are once you combine this optical modulation together with the thermal capacity storage together, so we can have the highest NH saving performance compared with the one, the blue one, which is only have solar modulation, which is optical modulation, and the low E glass, which is commercial one. Okay, so and also there's another thing which is a bit interesting. We also found that they have this.
Excuse me, Yi.
Yeah, this is last page.
Time for some questions, so it'd be nice if you could try and wrap up.
Yeah. Okay, it's all here already. So we have a compared with a double glazed glass, so they have a better acoustic reduction also. Okay, so this is acknowledge my student funding and my research fellow, and also this is the last one. This is our cover for this advanced energy materials. So we say here the best thing is combine everything on this window. We can generate the next solar cell, put the transparent solar cell here. We can even put a transparent battery here, can store the energy, and also most importantly, so we can have this chromic material smart window, so can save energy. So that's all. Thank you.
All right, great. If you could stop sharing, please.
Yeah. Yeah.
Well, it looks like our audience is very modest number of questions. There were two questions for Elise, had to do with the size of the material that you're using.
Yeah, I can answer that question. So the shorter answer I'll say is the nanostructures pretty much have to be as small as you can make them for the optical quality to be that high. Because just for reference, the metric that we use to really quantify, and for a material like aerogel, that is that very hazy kind of atmosphere look, we use a quantity called haziness. And glass, traditional float glass, is something on the order of about 0.5% of the light is going to contribute to this haziness factor. So that's really low. Prior works in aerogel usually sit on the transparent side of somewhere 8 to 10%. With the nanostructure that we've achieved, which sits on the order, I don't want to get too complicated into like how that light interacts with the pore versus the particle versus the interconnectivity versus the surface functionalation. But if you just said, give me one size that's pretty representative, you're looking on the order of, less than 8 nanometer diameter for the average feature size within that material is going to get you to a haziness that is comparable to glass at about 1 to 2%.
That's nice.
And there was a second question for Elise. It looks like you're popular. And it had to do with, again, anonymous question, and it had to do with how good is the mechanical properties of that material?
Yeah, that's a great question. So that has been one of the challenges of silica aerogel in particular, this glass-based aerogel, for a really long time, is that particularly for transparent applications, as I mentioned, those feature sizes, 8 to 10 nanometers is really, really small. And you've got, a glass material that is only 5% solid. So you've got a combination of a really brittle material, because it's glass and there's not a lot of material there. And you also have this nanostructure that has to remain very small. So the kinds of, hybridizations and functionalizations that you do to that material all contribute to higher and higher haziness. So at this point in time, our material is pretty fragile. I would say that it's kind of, our formulation in particular is on the order of, think of like a Lucky Charms marshmallow. So kind of a glass styrofoam, crunchy, breakable feel, but really strong in compression. So I didn't go into it in my presentation, but one of the ways that we've overcome those challenges is to really focus on incorporating at the manufacturing level, right at that step where normally we're taking, 2 panes of glass and sealing them together. If you do that with our material inside, we anticipate, because existing manufacturing does that step so well, we don't see those mechanical problems being a challenge, but it has limited applicability. So really appreciate that question.
And a question for all three of the panelists. The building industry, particularly in the US, but I think it's true in many other parts of the world, is one of the most conservative industries to deal with. They're not used to major changes in the way they've done things. And as a number of you have said, we're talking about a product which will have a very long life, at least 20 or 30 years, if not longer, installing in a building. How do we convince the industry that some of these breakthroughs, which are really very exciting, how do we convince them that in fact there's something that they should really think about installing? Again, we have the issue that we have the higher first cost, but we certainly have the payoffs in terms of energy savings. Is there anything? Years ago, I did work on foam insulation, and there's a problem of aging of closed cell foams, where their thermal conductivity changes. Is there any idea on how we could possibly do accelerated testing of our products to maybe under some extreme conditions to try and show the industry that they do have this kind of lifetime? And I'll just open up to all three of you if you have suggestions or ideas of what you, for example, Jan, in your vacuum insulation, that's always been a problem with how good are the envelope systems. How do you do accelerated aging?
Actually, this is specific testing in a climate chamber, which involves high level of the moisture content and temperature. What we introduced in that work, we figured out that actually in building applications, the major aging factor is coming through the temperature swings. If you take, for example, roofing or southern walls, you have temperatures well over what is tested in typical standard aging material testing. So what we try to introduce, instead of adding a couple hundred hours, we test for 400 hours the materials for aging. Instead of doing this, we are trying to introduce dynamic fluctuation of temperature and sometimes dynamic fluctuation of the moisture level. So that's adding durability. Very interesting discussion. It was part of the buildings one of the European conferences. I think that it was East European Symposium of Building Sciences. Somebody proposed, I think that from Delft University in Netherlands, or one of the Nordic universities, somebody proposed that actually is supposed to be added during the test delta T across the specimen. So there are many ways how people are doing this. There are some standard methods which are coming mostly from the insulation industry, which are not necessarily well work for the vacuum insulation. So that industry is growing, and testing is coming too. So that's.
Well, we always have the question of, we do these and we hope that that's going to do acceleration, but the question of is it double or triple the real time when we do these testing? That's something still needs to be.
Do you remember how difficult it was to estimate the standard testing for foam aging for many years? And still we ended up that we have different standard testing method in US, different standard method in Europe, and modified standard method in Canada. So it is exactly the same situation.
Yi, have you thought about that at all? How you've got some very exciting concepts that you've developed. How do you do the kind of testing that would convince people to incorporate that into long life buildings?
It is difficult, very. It is very difficult. Yeah, I personally found this commercialization is really difficult. So that's why I prefer to write papers. I'm just joking. Yeah, it's easier to write a paper, but much more difficult to commercialize, to convince people. So we have by the experience to work with industry people to get funding from government. And we're nearly there. Even the government say yes, the industry last minute say no. So we have all sorts of, yeah, it's difficult. It's very uncontrollable. It's not like paper, it's very controllable, but industrialization is very uncontrollable.
And Elise, I know we discussed that before, but how would you go about doing some accelerated testing?
Yeah, it's a great question and a big problem. I think, you know, part of what we definitely brought the research side of things, and I think we identified really early on that there was this list of questions. So one of the exercises we do when we think about, you know, is this idea worth pursuing as commercialization, is to think about, basically make a list of all the points at which our material or our product can fail. And what was interesting to me is going through that exercise, it turns out that it's accelerated testing. It's not just once you get the product, you start it, because by then you're already behind by the years. As you mentioned, accelerated testing, you know, it's still important to also have a full year cycle of just seasons, those kind of effects. Those can be really hard to get, you know, exactly the right conditions to make the materials. I mean, you know, intercompatibility, things like if we put our aerogel in, let's say that we didn't do a good job of making sure that the reaction when we made it was complete. And so it's got, you know, maybe some hydrophobicity or some chemicals that could outgas with time. And it might be worsened by the kind of silicone that it's, you know, made it up against in that seal. So I think that the approach that we've thought about is start the accelerated lifetime testing. You know, I mentioned there's a big team. There are a lot of great people working in this industry who have been thinking about these things for a very long time. So for us, we definitely looked outside for help there. But one of the pieces was start early, start often, and start at every level. So it's not just about putting the material through the ringer in our case. It's also about putting that demonstration into a sealed unit, doing it again with a frame, doing it again, you know, in the first version of lab-made materials, but then repeating those analyses and those verifications again, thinking about all the ways it can fail in every step as we scale up production. Because you just, you know, you can think you understand what's going on, but until you really prove it, I would say that that would be, yeah, that would be my suggestion for these technologies, is don't shy away from it. You don't necessarily have to solve all the problems, but I think identifying what they are, the biggest risks, and a plan for how you can test them is important and part of the whole development plan.
Mm-hmm.
Did you think, if I can add something, did you think about UV resistance, UV aging? That's probably one of the things to look over. Another one is just vibration resistance, because, you know, window work like a glazing works like a membrane for vibrations, for sounds coming from the outside. And those panes, you plan to put your product in between two window panes. Those two panes, because of thermal stresses, may not necessarily have the same resonance characteristics and may not the same displacement level. So you may have very, very high mechanical interaction between those two panes.
Yeah, and ideally, right, made worse by the better our material is at insulating, because the separation you get between those two panes of glass, you know, the better we do at insulating in extreme environments, right, it's seeing an even bigger temperature difference. So yeah, all of
mechanical situation much more different.
Yeah, definitely. I think that we think about them all interrelated. So we have individual, you know, standards or experiments planned throughout our development path to separate them out. You know, first tests like what happens when it's exposed, just the material itself, to extreme environments. But then there's also a test where in this form factor, how does that also, you know, how does the thermal and the mechanical, because those are not actually that separated, both in terms of the material optimization, but also in just the transport. Anything you do to change the mechanical affects the thermal and vice versa. So yeah, it really is a lot of things to be aware of. Yeah.
It seems like in so many of these products, it comes down to the edges. How do we deal with the edges and in these, as well as, you know, some people are trying to develop vacuum windows, and again the question is the edge seals and the thermal stresses and how they influence those. So that I think it's always going to be a problem we're going to have to deal with. Come up with some reasonable answers for those types of things. Yi, I had a question for you on the you recently have started to look at the thermal factors, which is really important in these things.
Yeah, exactly. Yeah.
And in the
It's very
summertime,
important.
in the summer times, where you were trying to reduce the solar gains to the interior of the building, one would think if you could find a process which made not so much made a window opaque, but made it reflecting. Because when it's opaque, what happens, of course, is the solar energy gets absorbed by the window system itself, and then there's a temperature increase, which it will result in some heat gain to the interior. Are there some technologies out there which we could, and in fact, you had that one sort of analogy to that animal that they had the reflecting surface. Are there some technologies which you could use which would increase reflectance rather than absorbance?
There is issue for reflective one, because reflective one only works for summer. But winter is also going to reflect. So you have to bear in mind, because we're doing the smart window, which means we need the thermal response or whatever response, optical response, which is completely the opposite for summer and winter. So for anything like that's not the reflective one, it works perfect for summer case, but winter there will be issue there, because especially in colder region, sometimes the winter even have higher energy requirements. So yeah, so that make the smart window really mean something, but there's a lot of problem there. So hopefully we can solve all these issues.
Well, I think the key is obviously to find some architect who's willing to try some of these technologies and in a demonstration building to show what the advantages.
It's really difficult. It's difficult. Yeah.
That's right. And of course, in all the cases, people are trying to get to zero net buildings, assuming that with solar collectors for PV panels on the top, we can do a good enough job on the technology as well as the controls, so that we could essentially say over a year's time, the net amount of electric energy the building uses is zero. And that's a goal I think we still have a long way to go to get something which is practical in all these things. What do we do? The last question I have for you guys, what do we do with older buildings in terms of retrofit? How well does some of these technologies work in retrofit? Yeah, and how well is your vacuum panel would work in a retrofit situation?
Actually, I must tell that the only projects I had on vacuum panels were retrofits. So that's something which I'm really excited about. I am also seeing great potential as long those applications are well designed from the building science point of view. Installation of vacuum insulation on the building is something which is extremely, I would say, different from regular practice right now in construction. You are adding to construction something which is highly impermeable and something which creates huge delta T across the building envelope. So if you put this inside, on the inside part, during the winter, whole outside part of the building is very cold. If you put this outside, you are exposing that internal part, for example, during the summer for condensation. So there is a lot of interesting processes which has to be taken into account. I can give you example. We did vacuum insulation on one of the walls in our building, Fraunhofer building in Boston, on the interior side, which probably all the building science so-called preachers would say that this is impossible. We did probably a couple hundred different levels of simulation, hygrothermal, thermal. We tested that detailedly all the bricks. It was a brick building, so all bricks were very detailedly tested for the hygrothermal properties. And based on this, we designed system we didn't fail for almost like 8 years. So it is possible, but it takes a little bit different approach and a lot of professionals, I would say that.
So for the smart window, so what we do is we just use a foam, just produce a foil to just stick on and take out. So this is one of the large research area in the smart window. Yeah, so it can be used in old buildings.
Yeah, I can just kind of speak to windows. It's a pretty tough problem for two reasons, because retrofit can either really mean, when you think about it for a home, it can either actually mean taking out your old window and putting in a new one, but that's actually considered like a construction project because of the necessity of getting that frame embedded in your home. And that also just makes it really expensive. But when you look at retrofit thinking, I'm going to leave my existing window in and either put an attachment, or maybe someday it's something like an aerogel film that you can attach. You have to think really carefully about how that gets in the home, its lifetime compared to its cost. But then the third thing is that windows, it's not just through the frame, it's not just through the leaks, it's not just through the glass. It's all of those things contribute to window losses. So sometimes even just taking, a film of thermal insulation and sticking to the glass isn't actually going to get at the real core of your problems. So I think it's a huge area that we need more work on is solutions for retrofits for windows. And I'll just make a nod that DOE ARPA-E projects, Shield Call has some really interesting focuses on trying to solve that problem. So hopefully we'll have something soon.
Well, I want to thank all three of the speakers for some really interesting, exciting ideas of how we move the staid industry forward to do something that's a little bit more revolutionary. The next webinar is going to be October 13th, and this is going to be a real feature with a number of panelists looking at the issue of future of concentrated solar power. Ossie Henry will be the moderator, and we have 6 people who will be presenting their views on this very important issue of concentrated solar power. Gang, do you want to have any final words?
No, I just say the website will stay open. So if you should if you have any comments, please type in the comments. Suggestion for topics.
Well, I want to thank our speakers again and our audience. There are a number of questions we have not got to, but we'll try and deal with them offline if we can.